So let me share my screen.
Okay, are we going?
You can see my screen, right?
Yeah, I can.
Oh, okay, nice. 我们可以开始了吗？我想问。
Who is in charge of the broadcasting?
Yeah, we can start.
Okay. Hello, everyone. I'm Bing Wang from Beijing Institute for General Artificial Intelligence. And it's my great pleasure to chair the 18th session of AsiaGraphics webinar. And today we invited two great speakers. They are Professor Taku Kumura from the University of Hong Kong and Professor Libin Liu from Peking University. In the following, they are going to introduce their recent works on character animation and simulation as well. So let's start the first one. The first talk will be given by Professor Taku Kumura. I think everyone in in character animation community know Taku very well. His work such as PFNN, MNN, and ManipNet are very impressive and have inspired a lot of many following up works. It also includes two of my works on camera motion control. And I would say thank you to Taku here. And in the very recent years, I'm also very exciting to find he also start to extend his work in the physical-based simulation field. I'm sure he will bring a lot of fresh ideas in the simulation community as well. Okay, let's welcome Taku to give us his talk, which is entitled Periodic Autoencoder for Character Animation and Isotropic Arab Energy using Cauchy Green Invariance.
Okay. So I should share my screen. And do this, and then I do that. Next, I share the sound, maybe. Share the sound. Okay.
Yeah, I saw the screen.
Yes, sorry, I misunderstood the time of it. I thought it's starting an hour later. Okay. Okay, hello everybody. Sorry for starting late. So thanks to Bing for the introduction. So I describe about two of our recent works, one about the motion synthesis and the other about this recent work about isotropic Arab energy. Okay, and well, we are, because just to give a justification of doing this research, because of the COVID, we were isolated a lot, and so we had to there was some demand for talking with your friends over the internet, and maybe you want to show your virtual avatar, and so we want to have so for doing this, you want to show your facial animation realistic, and you want to show some realistic character movements, which is the motion of your avatar. And also when moving around, probably you want to show realistic cloth deformation, which is the cloth you're wearing. And for this purpose, we also did some research about the facial animation, which is driven by the speech. Maybe I just show a quick video of this. So this is a work from last year's CVPR.
Sad white boy, perturbed woman, angry blue man and a green guy.
얼굴 애니메이션은 가상현실과 같은 많은 응용 프로그램에서 개발되었습니다.
L'animazione facciale è stata sviluppata in molte applicazioni come la realtà virtuale.
Sad white boy.
So that was the the facial animation part. But this is not described in this talk. So if interested, please check the paper. And so for today, I first talk about the periodic autoencoder for animating full body motion. So this was from SIGGRAPH last year. And then about this isotropic RF energy for simulating the deformation of objects. Yeah. And first I start from the periodic autoencoder for learning motion phase manifolds. This is the work done by Sebastian Stark and Ian Mason together with myself. And so here is a visualization of of the generated motion together with plots and phase manifold where the characters are moving. And you can see that kind of a periodic motion can be mapped to these in this phase manifold. And so here is showing these different movements of walking in different styles and like doing this football and also like the quarter motion as well as the dancing motion. Yeah, so this kind of like a time series model, it has been researched a lot in the machine learning domain. And basically we wish to like predict the pose of the character in the next frame using the pose in the previous frame. And lots of research has been done for proposing this kind of models. And when doing this, usually people talk about this, ambiguity in the future. So if you just try to like train LSTM or whichever simple, off-the-shelf model using these time series, the motion capture data, there's a chance that you have fall into some average pose. So that was, I think was usually known in the old days, yeah. And another thing that main issue that people don't talk much about this is about this transition motions are very sparse, yeah. So I think I talk about this in several places already, so you may be familiar. But for example, like you have like this kind of like a sidestepping motion and the running motion, which are in this visualized in samples in the high dimensional space. So these are red dots, and like the blue dots are of course poses corresponding to the sidestepping and the running motion. And then like you want to like put this into this time series model and learn these different movements, yeah. And actually, so the these blue dots and red dots, so they are for these individual movements like sidestepping and running. They are the samples are very dense, yeah. And so there's no problem when you are like synthesizing only the sidestepping motion or only the running motion, yeah. So because they're very dense, the system can learn the motions very well. But the problem happens when there's like a transitions between the movements. So here is like you use this something like a LSTM to like generate this character motion, and then you try to like quickly switch the direction which is going to correspond to some transition motion. Yeah. And so like the situations that, this transition motion is usually very, very sparse. Yeah. So there's lots of samples where there's like these individual movements, but the transition motion is very sparse. And when you like dump all these samples into the neural network, actually, they don't know how to do the transition between the movements. Yeah. And then they just simply blend between some of the samples, and then the results appear bad. That's one interpretation of the problem here. Yeah, so for coping with this, like introducing this phase label was one thing that we've been considering. And so like you can define the phase as when the right foot landing onto the ground is 0, and then left foot landing onto land is pi, and right foot landing onto the ground is 2 pi again. And then you can like this kind of a rule is very consistent between all kinds of locomotion. So the sidestepping and running and walking, they always follow this kind of a rule. And so this is useful for like when you have this kind of a different kind of like locomotion, you can have these phase labels added, and then you can do some find the correspondences between the poses. Yeah. So then it's going to be easier for the system to find which pose corresponds to which and how the transition should happen when this transition is happening from the user control signal. Yes, and so that's how we were, one of the merits of this phase function neural network that was proposed by us a long time ago. And so here it was like the neural network weights were like, what function by the phase variable, and using the phase of these control points, which are all in the form of this and this network weights, are interpolated to like calculate some specialized weights for each phase of the locomotion. Yeah. And so, so that it's a time series model. So the next pose is predicted from the previous pose with the user control signal. So that's how we've been working on this for producing this kind of a locomotion. And we also did the similar work for like interaction of character with environment, and also like for like more complex movements like this kind of a basketball. We could like define a phase for the context between the individual limbs and the object or environment. We also did some motion stylization based on this idea. And so the problem is like, in all these examples, we had to like, define this phase variable. So for the locomotion, it was like this left foot, right foot contact. And also for this kind of interaction with the environment, it was also defined based on the contacts between the body and these objects. Yeah, so same for this basketball. So like defining this kind of rules for the phase is something that is somewhat manual, so which is not very great. So in this periodic autoencoder, we were trying to overcome this limitation. So by like trying to learn these kind of phases automatically from the motion capture data. Yes, so the procedure is that you give this kind of like a all the motion capture data in the form of the joint velocities, and sorry, the joint position, yeah, the 3D joint velocities, and then we pass it through the convolution layer, and then we do reducing this dimensionality, and like for these smaller number of channels, we apply this defined FFT. To compute like these parameters and the frequency domain, which includes like the amplitude and the the offsets, and also like the and also like we have another small and also the frequency, sorry, and then they have another small network to predict these phases within these motions. Yeah, and then so they are converted into the frequency domain, and then you can use the sine cosine functions to like reconstruct the the motions in the feature space, and then do the deconvolution to reconstruct the motion again. Yeah, and then by using these parameters that are in the frequency domain, we can like try to construct a latent space. So we call this the phase manifold. And if you plot these samples using PCA, then you can see that the motion appears more nicer in this phase manifold, which are shown in the bottom. Yeah, and so was now so the claim is that it's going to be like easier to search for motions or use these parameters. By using these parameters for the time series model, we can like synthesize motions more and nicer. Yeah, and also like by analyzing these kind of movements in this phase manifold, we can like see various cyclic features of the motion. So if it's like a ordinary locomotion, you will see a single cycle. If it's like a motion where you have like two cycles, like arms rotating while walking, then you will see this kind of two cycles. And finally, if it's like a random dancing motion, you will see like this kind of like multiple cycles, randomly intermoving. Yeah, and so So now we can use these phase variables or like the frequency domain variables as additional input for the time series model. So these are going to be like the input, and then we can predict the next pose. And these parameters in the phase manifold are also predicted, and so we can do some time series recursive recurrent motion synthesis. Yeah. And so let me quickly show some of the results. So these motions are like this kind of like football, or like motions in different motion styles, and quadruped and dancing. And so here's the visualization of the results for this locomotion and quadruped. And so you can see that the motions and these different styles. Yeah. And so for the for quadruped motion, like you can see that there's a tail motion and the motions. And if you use these, we use the previous approaches, tail movements tend to be less vivid. And by using this phase manifold, we can have like a good vivid tail motion. And here's another example of like doing some running and different styles. And so you can see that our system can like handle different styles of locomotion. And so if we use the PFNN, we could have issues with the motion of synthesizing like the arms because if the arm movements are not really following the phases of the legs, then the arm movements can be more ambiguous. Also, it couldn't handle like this kind of like a motion where the legs are not moving in a left and right alternate pattern. And so here is another example of doing this kind of a football. And you can see that the ball is like responding to the motion of the legs, and then it's somewhat like the ball motion is actually generated by physics, and it's like moved based on the collisions between the legs and the feet. Yeah. And finally, showing this kind of like a dancing motion where the character is like responding to the dance movement. And so the sound features are the frequency features are computed and used as additional input for the motion synthesis. Yeah. And so here is the dancing compared to the baselines. You can see the motion quality is better with the proposed method. And well, although it's less creative, yeah, actually it's the motion that the pattern can be created is just limited to those training data. And but you can see that the dance motion can be a different dance motion appears when the music style changes. Increase the sound a bit. Yeah, so. You can see that when the music is more is slower, there's different movements appear. Yeah, so in summary, so here we propose this new approach of this periodical join encoder, such that we can compute these features in the frequency domain. And so they're actually also a good feature useful for motion matching as well. Yeah, because the motion is the features are in the frequency domain. Actually, it computes some feature of a longer window of motion, so it's not just a feature for that individual moments. Yeah, and so that's pretty much all for this part. And now let's go to the next one, the isotropic R-up energy using Cauchy-Green invariance. And so this is, the work done by Huancheng Lin and Floyd Chitalu and myself. Yeah. And so, so we wanted to like simulate these deformation of the objects, like doing this kind of like a cloth simulation. And so, yeah, so we think, well, better Yes, hurry up, yeah. And so like computer animation and robotic, we want to like sometimes like this kind of like interaction of the cloth and the robot and human. And so yeah, so we wish to like have a good a fast simulator for doing this. And also it's better that it's stable. So those are like one of the motivations again for doing this kind of research. And so for doing this, the procedure is that we first define the elastic energy, and at every iteration we compute the energy gradient and the Hessian and like this. And then we are going to like yeah, so this is the steps that we go through. And then we calculate the displacement by solving this linear equation where this displacement is the P and G is the gradient and H is the Hessian. And then we update the particle positions based on this, displacement. Yeah. And then we will be able to like calculate the location of the vertices in the next frame. Yes. And so when doing this, so the cloth is going to go through this kind of like deformation, and then this deformation is going to be represented by this, this what's a deformation gradient? Yeah, this F. Yeah, I think you guys know well about this. Yeah, and so using this deformation gradient, we can define different types of energy, like the RUP and STBK and Dirichlet and Neo-Hookean. All these kind of energies exist, and so you can see that they are basically like checking this, based on this deformation gradient, yeah, and so there's something called this Cauchy-Green invariance, which are based on this, based on this multiplication of this transpose of the deformation gradient in itself. And so this, there are three deformation gradients. Yeah, actually there are more, but here we focus on these first three deformation gradients, and these are very useful for like, well, when you are trying to do this calculation for the gradient and the Hessian. Yeah, so as I mentioned, we need to calculate the gradient and the Hessian for updating the position of the vertices. And so when doing this gradient calculation, so we can, use this equation that is coming from the chain rule. And so by using this, what's the Cauchy-Green invariance, so the calculation of the gradient and the Hessian can be simplified a lot. Yeah. So for example, for this calculation of this gradient, if the energy is this Dirichlet and or the Neo-Hookean, and you can like the energy can be written by easily by these Cauchy-Green invariants, and then you can like just do some derivation of these with the Cauchy-Green invariants. Then the equation of the gradient becomes very, very simple. Yeah, so this we can do this kind of a mix and match. Yeah, and so for each of these energies, we can just simply derive them by the invariance, and then the gradient equation becomes very easy. As we can do the same for the Hessian as well. And if it's like energy like STVK, again, the energy can be easily described by these Cauchy-Green invariants. And again, we can do this mix and match thing so that it becomes the equation becomes very, very simple. Yes, and so the same for the Hessian. And on the other hand, when we do this with the RUP energy, actually we are going to face some issue. Well, before going into that issue, so this RF energy is actually very popular for this kind of shape formation or texture mapping or shape interpolation. As you know, it's been going on for decades. And but like if we want to do this mix and match thing with the RF energy, we are going to face some problems. Yeah, so you expand this RF energy, and then it becomes like this, and then you can replace this one with the Cauchy-Green invariance, and this one is simply the dimensionality, but this trace term is going to remain. Yeah, so this one remains, and you can see that this is difficult to be replaced by the Cauchy-Green invariance. Yeah. And so then we don't know how to do this mix and match thing, right? So because of this trace term, yeah. So that's an issue, And so, so people have been believing it's impossible to like replace this, write this trace term with the Cauchy-Green invariance. Yeah, and then my student Huan Cheng was playing through the math. And so in fact, these Cauchy-Green invariants, you can rewrite them by the singular values of the, write them in the form of the singular values of the deformation gradient. Yeah. And so you can see that they can be written like this kind of like a polynomials of the singular values. Yeah. And so then actually the trace term can also be written in this by the singular values like this. Yeah. So that then it becomes a bit clear why it's difficult to write the trace term with the Cauchy-Green invariance, because the trace term is just the summation of the singular values, where the Cauchy-Green invariants are all high dimensional polynomials. Yeah. So then it's like, but like actually you can then do something, play around with the math. And so we can first like do some we can square this equation on the right first. Yeah. And then it's going to be like, you can this part becomes squared, and then actually we can replace some of the parts with the Cauchy-Green invariance, and then it becomes like this. And then you can square it again. Actually, you square it again, and then you notice that all the terms can be replaced by the Cauchy-Green invariance. No, not all, but more terms can be rewritten with the Cauchy-Green invariance and the trace term. Yeah. And so like after all, it becomes like this. We come up with this kind of like a fourth order, polynomial of the trace term. Yeah. And then all the rest parts are like the coefficients and the constants are the Cauchy-Green invariance. Yeah. So this is like a equation where of the trace term and all the rest are the Cauchy-Green invariance. And then so in fact, so this kind of like a fourth order polynomial, we can use this the Ferrari's formula for calculating the root. Yeah, so we can solve for this root, this trace term actually. And then we will after all, it's going to be like using this root of this fourth order polynomial, we can rewrite this R up energy by the Cauchy-Green invariance. Yeah, so the details are not shown here because the equation is too long, but there is a analytical solution for it. Yeah, so that's represented by this F. Yeah, here. Okay, and so after all, after this analysis, now we can actually do this mix and match thing, so we can like derive these R up energies using the three Cauchy-Green invariants, and then we can like come up with a simpler equation. Yeah, and then we can easily calculate this gradient and the Hessian with these Cauchy-Green invariants. And so it becomes like this. And so after all, what we have shown here is that the the R up energy can be written by the Cauchy-Green invariance. Yeah. Another thing that we came up with through this research is that we came up with an analytical solution for decomposing the the deformation gradient into the rotation and stretching term. Yeah. And so previously, when doing this decomposition, we had to do this SVT, and so that requires some iterative calculation, and also there was some issue with the parallelization. Yeah, so because it had to be mostly, it was easier to do it on the CPU, so the data were passed to the CPU for doing it, and then you have to transfer back. Yeah, so that was a bit annoying. But because we can write this rotation matrix by the partial derivative of the trace term with respect to the deformation gradient. Actually, we can do something like the mix and match thing. Not mix and match, but the chain using the same chain rule, we can rewrite it like this. And because this f was the root, which are written in the form of the Cauchy-Green invariance, we can have an analytical solution for this. Yeah, so we can have the analytical solution for this. So after all, the rotation, we have an analytical solution for them. Yeah. And so we can calculate the rotation matrix without the SPD and polar decomposition. So actually, this is going to be faster than the other methods. Yeah. Also, because the roots of this fourth order polynomial can be written in this form of these for the singular values of the deformation gradient. Actually, we can have a closed form solution for the singular values of the deformation gradient, which can be useful in some cases for some energy or doing some finite element analysis. Yeah. And so that's also good. And so let me show some quickly show some examples of using this for like simulating this kind of deformable bunny. And also here's another example. This is the same example, sorry. And this is another example. And pulling this bunny in different directions, and like here is what the stress test with this these points of this box are randomized in the very beginning, and you can see that it can stably do the simulation of this kind of like randomly vertices. Yeah. Okay, and so here's another example of simulating the cloth. So it's a pretty simple example, but you can do these kind of things. And also you can do the shape interpolation, also all things that you can do with the RRPG. Now you can do it, well, it's doing the same thing, but using this analytical approach, we can do it more quickly. Okay, and now because we have like shown that the RP can be written in the form of this Gaussian-Green invariance, we can like simulate objects with different energies simultaneously more quickly, using this mix and match thing. Yeah, so you can show these simulations based on different energies, and it can be done quickly. Okay, and so regarding this rotation, the calculation of the rotation and stretching from the deformation gradient, actually it's this operation, I think it's used very often in various situations, and you can see that our method is faster than the existing methods. Compared to the state of the art, it's 1.7 times faster. Compared to the eigen library, it's 3.78 times faster. So that's useful. I didn't put up the website in this slides, but you can search for the title and you can download the code. So if you're interested, please give a try. Okay. And so in summary, so we have shown that the RRP energies can be represented by the Cauchy-Green invariance, and we also had a closed form solution for the rotation singular values of the deformation gradient. And so thank you very much for listening. So these are the students who were involved in the research. Thank you very much.
Thanks so much, Taku, for your excellent talk. Maybe I can take the privilege to ask some question. So about the first paper on the periodic autoencoder.
Yes.
Could you explain when you extract the features in the frequency domain, how to align the motion and do the interpolation, like the transition of two motions?
Okay.
I'm not really get the detail here.
Right. So the interpolation of the motion is actually just what's happening naturally. So the point of this one is that it's like computing some features the feature maps. So it's going to be like these kind of like, it's going to be the dimensionality is reduced. And so each of these, these curves in the lower dimension, they are converted into this frequency domain. Yeah. So actually, these motions are somewhat represented in a low dimensional, space where the variables are like these, these parameters in the frequency domain. Yeah. So like the amplitude, this frequency, and this offset, this kind of parameters. Yeah. So the thing is that we're thinking that the motions are, these kind of like underlying frequency domain, lower dimensional parameters in the frequency domain are automatically extracted, where it's like representing which are forming some basis of the movements. Yeah. And so this kind of like a pattern of the repetitive pattern is automatically extracted. And so by like, synthesizing the motion in this space, we can produce nicer movements that considers the nature of the movements. Yeah.
I see. Okay, so because you learn different kind of motion together, then you find a common like reduced space, which can represent like different kind of movement, and then you can do the interpolation on each like basis, right?
Yes.
Okay, I see.
Yes.
Okay.
Well, that's one interpretation. Yes.
I see. Okay. So if there are some like rich contact happens, did you see there any problem for like very limited number of frequency?
Right. Yeah. So the motion that involves the contacts are mainly like the quadruped locomotion, and which were the other ones? I think the other ones are also still like the locomotions that we've seen through, and so if it's it's probably a good idea to try with these contact-rich movements like the basketball, or like like the sitting on the chair. Well, basketball is probably interesting because there's lots of high frequency movements there. It's if it can reproduce these movements, that's better. At this moment, we haven't done such experiments, but that's definitely good to try. Yeah.
I see. And do you think this kind of framework is suitable for the manipulation task?
Oh, the manipulation task, yeah. So that's a good question. So, like, I think in general, these are better for like these repetitive movements where it's like there's there's lots of periods and phases are involved. For the manipulation, it's difficult to say, I think. Yeah. So, well, actually, yeah, because we were previously trying something like the local phase representation for the manipulation when handling the ManipNet data, and in that case it wasn't working so well. So it's like because the hand motions are a bit different from like these locomotion data, because the contacts happen very quickly, and like the coordination between the fingers happen in a bit different way from locomotion. So it's a bit difficult to say. I think it's interesting to give a try for that too. Yeah.
Okay, thanks. And another question for the second paper. I saw you use the invariance as the variable to formulate, like to give a unified formulation of the elasticity energy. I know there are some work that directly use the principal stretch, like the eigenvalue, as the variable to formulate all kinds of like elasticity energy. So what's the like benefit we can gain from using the invariance rather than the eigenvalue?
So like that's a very difficult for me to answer. Yeah, this one, yeah. So it's I'm still just learning from my students in Norway's and like Florida, Beijing and Florida and Quebec. But is that what? Well, one thing that you can benefit from this from this research is that this you know this analytical solution for this decomposition, yeah, for the rotation and stretching, yeah. So because we have like the analytical solution, we can directly calculate the stretching, you know, from the deformation gradient, which is going to be faster, and also like so you can like use many energies are, I think, based on this stretching term, and also like the singular values are so because we have these analytical solutions for them, you can like, you know, quickly obtain them without this recursive calculation, and so that's one of the benefits. Yeah.
Totally differentiable, right?
Yes. Yeah. So I think that it's also useful. Yeah.
Yeah, maybe it can be used for the material interference, some task like this, like the inverse learning task.
Yeah. So hopefully it's used for such purpose as well.
Okay, thanks so much. I think the time is almost there. Yeah.
Yeah. So I will stop the sharing and pass it to Libin. Yeah.
Yeah. Let me share my.
Okay. Yeah. Thanks, Taku, for a very nice work. Yeah. Actually, I had a question regarding the first work. Then like this is a series of work down the road. Like you keep finding new factors and related to the animation, to the period of animation. Actually, I really want to know what's the next potential factors for this.
So hopefully it continues, but I'm not sure. Okay. Thank you.
Yeah.
Okay. My screen is shared, right?
No.
No. No?
Yeah.
Okay. So let's move to the next talk. The next talk is entitled Co-Speech Gesture Synthesis and Generative Motion Controllers. The talk will be given by Professor Libin Liu from Peking University. Actually, I have known Libin for many years, and he got his PhD degree from Tsinghua University. And now he's a assistant professor at Peking University. And his research have been recognized by multiple awards. Particularly, I want to mention here is one of his most recent work won the first SIGGRAPH Asia Best Paper Award. And he will also introduce this work today in the talk. Okay, so let's welcome Libin for his talk. And I will stop sharing.
Yeah, let me sharing my screen. Okay, can you see the slide playing?
Yeah.
Okay. Yeah, thanks, Bin, for the very warm introduction, and hello, everyone. So in this talk, I will discuss two of our recent works, like both learning generative models to create realistic human motions. One of the work is like using speech signals to drive the character to perform co-speech gestures. And another work is using physics-based simulation that help the character to achieve more realistic interaction with the environment and with unpredicted perturbations. So both of the two works were both published in SIGGRAPH Asia 2022. Yeah, in my talk there were a lot of videos and animations. I'm not sure if my bandwidth, my internet bandwidth is good enough for those videos to play. So if you're interested, so feel free to just visit my website, and there's a list of these videos if you want to look. So I think the motivation was no. I think Taku has gave a very nice review of the previous works in animation. So here I just briefly review it. So the motivation is actually from the digital character, the digital humans. We have seen a very good progress in the past few years. Then there's a lot of companies has published their works to create a very realistic human motions. So I think the human motion, the digital human, and the techniques behind the digital human can be categorized into 3 different categories. The one is the appearance, and which is thanks to the progress of rendering technique, the graphic technique, we can now achieve very realistic appearance for these digital humans. And then for the language, for the interaction with the character, now we know ChatGPT, right? It's very popular in recent days. So it can. I also know that there are some game designers who are trying to integrate ChatGPT into their design so that they make their NPC or their avatars to be more interactive to the users. So I think the language development is also dramatic, very fast in recently. And the last is the behavior. I mean, it's related to the motion. This one, because I'm doing character animation. So from my point of view, I think the behavior, the study, the techniques to create the behaviors for digital characters is still fall behind the progress of other domains. So we can see, like for many companies, they have published their digital human products, but to achieve realistic digital human motion animation, so there often requires a person behind the digital character, like who performed the motion to dance, and then the motion was captured using some motion capture devices, and then transferred to the digital to the character. So there was always a goal that for character animation, especially for the research in character animation, that can we train a model like ChatGPT, right? That using a lot of motion data and then use a model to create the realistic motions. So we do not need a person behind the character to perform those motions. And we hope these models can take some control signals as input and generate these motions that fit the requirements of that control signals. So this long research has been studied in the past decades, and until very recently, maybe 5 to 6 years ago. I think that the first work was done by Taku, the PFN. Then it's the first paper, the first technique I know that can generate appealing results by only training on a set of data. But in more recent years, we have seen the applications of generative models, various generative models, from VAE to normal flows to GANs, and more recently we have seen a method using different models. So the control signals of the early works all use game controllers to provide like a direction of the character and the control signals, and now there's more works trying to use higher level descriptions, like we can type some descriptions using natural language, and then the model can convert that into a short piece of motion. So I can imagine that this long research can go very fast, and maybe in the next few years we can see like we can just input a script, and then the character automatically performs and scripts, and it becomes a movie. So I believe that will happen very soon. But here, this talk, we just the first work we are going to discuss is a specific area in this motion generation. So the goal is to the input, the driving signal is the audio. The scenario is like, for example, when I'm giving this talk, I'm just speaking, and I will do some gesturing while I speak. So this is a natural. So people often do this. intentionally or not or unintentionally, just like they're trying to convey more information using gestures. So the goal is like how can we recreate such gestures based on the audio input. So this is the problem, and we have created pretty good results. So this work was published as a paper. The title is long. I just don't read. So if you're interested, feel free to take a look at the paper. And we are very lucky this year. This paper was selected as one of the 4 best technical papers, and so it's quite exciting for us. And I think it's a very good direction to go. And actually, we know this gesture is a very important part of speaking. So when we're doing gestures, we add emphasis and clarity to the speech. So gesturing, the automatic generation of gestures has very important roles in many applications, like games, like digital humans. And also there are some very interesting related areas, just like there's online shopping services. They use virtual avatars to help them to sell goods. So this automatic way to generate motions is also helpful for them. So the formal definition of the problem is like we want to create a gesture synthesis system that can take several modalities of speech, like including audio. That is definitely the most important, and also possibly the text transcripts of the audio. Now, actually, this is not a very hard task in nowadays, because the speech to text technique becomes pretty mature. Now, even for now, I know some people are watching this talk on Bilibili. There's a realistic translation. They can translate my talk into text. So this is actually not a very hard task. And also sometimes we can take a special styled indicator, just like to specify which people who is talking, because different people may have different styles. So we take all this information as input and try to create a gesture animation that seems naturally accompanies than a speech. So this is actually a very long term study. Like the earliest study can be dated back to 30 years ago. So basically, I think the history of gesture generation is almost the same as the history of character animation. Because basically, people just trying to use the technique for these specific tasks. So the earlier days, where people using were using state machines combined with handcrafted rules. And later we start to replace the rules with probabilistic models or statistics models. And then with the development of deep learning, there's work to start using deep network to learn a end-to-end generator that directly map audio input to the motion. But there's always a problem from the previous motion generation method. The first disadvantage is the quality. Like we find that the end-to-end training always generates some averaged motion when it applies to audio that was not seen in the training. So this problem is definitely very, very challenging. But there is we can do some analysis on the problem, and we think there's two aspects is very important. The first is the rhythm. So like if we see a person who is talking while gesturing, like Obama, we can see like there's a quite consistent there correspondence between the rhythm of the motion and the rhythm of the speech. So that makes this problem very similar to music to dance generation tasks. But different from music to dance, for music, we know that it has a very clear rhythm structure that can be easily identified, and to use that to constrain, to help the generation of dance. But for gesture, we know the rhythm is not stable. Even when I'm talking, the stress of my voice, no, it's not a consistent pace. It's just a changing all the time. So it's very complicated to make this. This becomes a hard task to make this motion, the rhythm motion, to be consistent to the rhythm, the audio. Actually, there's one preliminary results experiment we have done before, where we try to let the character do some random motions, but we manually align the motion, the stress of the motion to the stresses of the audio. So even that is random motion, we feel that the motion accompanies the speech pretty well. The only problem is that it do not have semantic meanings. So that also suggests that to make the rhythm match to the audio is a very important part of naturalness for gestures. And another problem is the semantic correspondence. So like for gestures, I mean, it's different from sign language. For gestures, we know the correlation between the gesture motion and the audio is very weak. For example, different people, or even the same person, they can use different gestures for the same words. And also, when they perform the gestures, the time when they perform that gesture and the word they wanted the gesture to accompany is not perfectly temporally aligned. So this actually make the problems a many-to-many mapping problems. So then also make a naive end-to-end learning algorithm hard to learn the mapping between the two modalities. So in this work, we were trying to overcome these two problems by explicitly disentangle the semantic information and the rhythmic information of both the speech and the gestures. Now, after this entanglement, we then try to build. We believe that the relations between the two modalities, the two modes, are easier to learn, and then we can use some learning techniques to build such relations. So for the rhythm, the idea is very simple. So we can talk in a single slide. So we know that the input gesture, the input audio, it has a changing pace. So we can use some simple techniques. For example, we can identify the onset of the audio input and use that as the indicator of the beat. And based on that, we can normalize the duration of this segmentation. We segment the audio based on the onsets and then normalize them into the same length. And after that, we can convert each of the normalized audio sequence into the normalized motion. So at this point, we think that at least the motion and the audio are temporally aligned. So it's make the generation easier problems. And after generating these motion blocks, we can apply a denoise process to make the motion back to the same rhythm of the audio. Of course, this can introduce some artifacts, so we will apply a Gaussian filter afterwards to make the motion smooth. So this is how we build connections between the rhythm part of the two modes. Sorry. And for the semantic part, that is more complicated. That is, I think, is the most interesting part of this paper. So we actually take a look at some linguistic theory, and in the linguistic theory, they actually study a lot about how humans perform their gestures. So they have some conclusions. One of them is like the gesture motion. It consists of a sequence of gesture phases. Now, this gesture phases aligns with the intonational units of the audio. So this gesture phase is often referred as a gesture lexeme. Actually, we actually abuse the word, the gesture lexeme. We use gesture lexeme to refer to a small cluster of gestures that are similar to each other. So like, for example, here, we know each of these colored cluster is referred to the gesture lexeme, and that will be corresponds to the segment, to the intonational segment of the audio. And then within each of these cluster, we can see there's a small variations between the motions. And we'll assume that each of these motion, these motion variations is controlled by latent variables, and then we call it the gesture style codes. So this is how we formulate how we model the gesture motion. And then we with some further relationship between the gesture motion and the audio. So we assume, and this is not only we assume, actually this has some linguistic theory background. So they say that the gesture lexeme usually related to the high level semantic audio. So it generally it corresponds to the semantic of the audios. And also the gesture style codes, I mean the variance within each gesture lexeme is related to the low level acoustic audio features, just like the stress, for example, and the pitch, something like that. So based on this assumption, the semantic part is done by like first we have a number of gesture motion examples. We first construct a gesture lexicon, basically a gesture vocabulary, by clustering them into a number of gesture lexemes. And then we then disentangle the audio into high-level semantic features and the low-level acoustic features. And then we can build connections. We can build the mappings between the high-level semantic audio features to the gesture lexeme, and the low-level audio features to the gesture style codes. Now, basically, and this then defines the motion variation, and then convert those motion descriptions into the actual motion. So this is the overall system. The first problem is how we can create the gesture lexeme, the gesture lexicon. So instead of applying clustering and the KN clustering algorithm, this kind of basic techniques, we actually employed a very powerful network structure, which is called a vector quantized VAE. It's a VQ VAE. So it's different from the traditional VAE. You know, for traditional VAE, we have an encoder, then encode the motion into a latent variable, and then decode that variable into the motion again. For the VQ VAE, we replace the decoding process by first finding the nearest. So we first have a code book, which contains a number of vectors, latent vectors, and then after we encode the motion into latent space, we find the nearest code from that code book that is nearest to the latent representation of the motion. And then the decoder will decode and code into the motion. So this way we actually automatically this VQV setting first quantized the latent space. The latent space was a continuous space, and now we quantize them into a discrete set of codes, latent codes, and we find that each latent code naturally corresponds to a cluster of motions, where the motion in each cluster are similar with small variations. So like this after training this VQVE, the code book becomes the gesture lexicon of this work. So after that, now the next problem is how we can disentangle the audio features, the high-level audio features from low audio features. So achieve this using a contrastive learning. So basically, we train a deep audio encoder. So basically, it has many convolutional layers. But to disentangle the high level, we consider the features at the end of this encoder is high level features, and all the intermediate features of the out of the intermediate layers and the low-level features. So the contrastive learning is done by, like first, we also have a text input, which can be considered as the anchor of the semantics, semantic representations. So we're trying to make the high-level features as close as possible to this anchor, to the semantic features extracted from text. And in the meantime, we're trying to make the low-level features as far as possible from that anchor features. So this actually encouraged the high-level feature contains the semantic features, and the low-level feature only tries to only capture the semantic non-semantic features from the audio. So actually, after done this, we found some very interesting results. So this is our motion latent space. We cluster the motion into this space using VKVE. And then we can, after we train this audio encoder, we can cluster the high-level audio features using nearest neighbor, using KNN. And then we find that for each of these audio clusters, it corresponds to a set of semantically similar words. And also, we find that each of this semantic similar cluster, it will correspond to a small number of motion clusters. In the meanwhile, if we do the same for the low-level audio features, we find that each of the low-level audio feature cluster will correspond to a lot of almost every motions. So it also suggests that the high-level feature, after we do this clustering, this high-level and the low-level audio feature disentanglement, the high-level features defines the gesture, what the gesture cluster it will use, it should use. And the low-level feature, presumably, it defines the variations within each clusters. That is basically the idea and the results we have seen in the preliminary results. So here are some results for some examples for the high-level feature clusters. So
there are so many people.
More monkeys are here.
So you can see these few words as semantically similar. They are using these few clusters. And for the other semantic similar words, they will correspond to a different set of motion clusters.
No water, no food.
Never give up.
Okay, and then after this, we have decoupled the high-level features of the audios and the gesture lexeme and gesture codes, and then we just simply learn a neural network to map given input audios map the given input high-level audio features to the lexic gesture lexeme, and low-level audio feature to the gesture step codes. And to get a better results, we test our method on 3 different data sets, and to get a good result, we actually collect a Chinese gesture data set by ourselves. And here is an example where we use Obama's speech we found on YouTube and generated motion. This audio was not seen in the training data.
I am here with students at Wakefield High School in Arlington, Virginia, and we've got students tuning in from all across America, from kindergarten through 12th grade. And I am just so glad that all could join us today, and I want to thank Wakefield for being such an outstanding host. Give yourselves a big round of applause.
Yeah, you can see that the rhythm and the semantic matches the input audios pretty well. And also, although we train these models on English and Chinese data set, it can automatically transfer to other language. Like we can use a French input. I'm sorry.
De manière culturelle, artistique, sociale, mais aussi émotionnelle. Aujourd'hui, on se demande encore comment est-ce que tant de gens sont venus et sont revenus.
And also the system can be extended, like we can add an extra codes now in addition to the style codes to control some high level, some detailed motion features. For example, we can use them to control the height of the character when it performs a gesture. So here's a very simple example.
Straight and kind of...
So this is we let the character use a lower right hand, and this one we let the character to have a higher right hand, so you can see the difference.
And there's this fantastic thing where like my dad made some sort of like inappropriate joke or something like that, and I just straight.
Okay, so as a conclusion, so this work we present a rhythmic and semantic aware cosmic gesture synthesis system. So we actually explicitly disentangle the rhythm part and the semantic part, and also it disentangle the high-level features of audio and the low-level feature of audios and the corresponding features of the motions. By explicitly build connections between these correspondences, we can create a very nice audio outputs. Sorry. So the motion generation, the method we discussed about before is mostly called the kinematic method. So they generate motions without considering the physics of the world. So that actually it can cause some artifacts such as foot skating and penetration with the environment, and also for the more for interaction with the environment. For example, like this few examples. The kinematic method it becomes very difficult for the kinematic method to generate this kind of unseen motions. Because for kinematic motion method, we usually need data be captured, and then we can generate the motion based on the kind of signals. For this kind of motions, especially for the unpredictable perturbations from the environment, it's very hard to capture the motion, example motions. So that makes this kinematic method very hard to create a motion for these scenarios. So the solution, we always think the solution is the physics-based animation. So we're trying to replace the generation process with a physics simulation. And so we're trying to reproduce the ways that real animals create their motion in real world. So the problem here is that we need to create a controller, motion controller, then it applies, then it computes the actions, for example, the muscle forces, the joint torques to activate the character in this simulated environment. But this motion controller is very difficult to create, to design. So that actually makes this physics-based method. We always permit that the physics-based method is the next generation of animation techniques. But after 20 years from the first work, or 30 years from the first work in this direction, there's still no games actually really use this technique. So the difficulty is always the motion controller is very hard to create. So now in the past few years, we have seen a very good progress in reinforced learning, especially the deep reinforced learning. So we know the technique is the idea is simple. We just like the character to interact with the environment and using the environment's feedback to update this policy to compute their torques or muscle forces. So using this method, we actually can achieve very good physics-based controllers by tracking reference motions. So, but there's one problem. So we can see there has been very good results, in the past few years, from the basketball to the soccer dribbling, and to very, very complicated tasks that they can achieve all these very nice works. But the problem of this traditional IR method is that we always need to retrain the policy for each of the tasks. And every time we train a policy, it takes quite a long time to finish. Usually at least a few hours. For more complicated tasks, it can go to days to finish. So there's a question regarding to this problem. we know for the motion, for the kinematic method, we can train a generative models, then it can automatically create, and then it can learn a number of motions, and then use all this knowledge to create motions based on the control signals. The problem is whether we can convert the same idea to the physics-based animation. That means, can we create a generative motion controllers that can learn a large number of motion scales? The answer is yes. So we have seen a few works in the past few years that learns motion embeddings or motion primitives from a number of motion examples. So after learning, we can generate samples from we can sample from that motion primitives, and then use policy and simulation to create the corresponding motions. But the problem of this training is that to train the control policy, we needed to let the control policy to compute a activation for the character. For example, we can compute the jump talk, and then we implement the jump talk into simulation, and then to compute the next stage, and then it becomes a reward. And then we need to use that reward in the IL framework. We need to use that reward to compute the improvement direction for the control policy. But the problem here is that the simulation engine is often considered as a black box. So which means we cannot directly compute a gradient through this simulator. So the previous work already used some techniques to sidestep this problem. For example, we can use a number of motions. We can use behavior clonings, which completely get rid of simulation, or we can use like model frame learning that basically the typical IL settings. It's a model free method. So the problem of this work is like if for the behavior cloning, if we get rid of the simulation, we cannot guarantee the learned motion is physically correct. That will degenerate the motion quality. And also for the model frame method, we know it needs a quite large number of samples to compute the expectation of the simulation. So that's also a waste of simulation. And also, because IL, reinforcement learning, is not a very stable process. And for model frame method, for example, the MP and the ASE, they are using the GAN, the GALE, basically adversary training. So that is also another unstable training process. So these two training processes combined can make this problem a bit hard to tune. I mean, if it works, then it works. If it don't works, it becomes a problem. So our solution. So we thought we take a look at the human. Like for a human to learn emotion, they don't really have a very accurate sense of the physics of the world. Instead, it has a very rough approximation of the world. So they can use this approximation to predict what's the results of action. And use that, based on that, it can keep improving its skill, based on this imagination using the word model. So the second work of this talk, I'll go this very fast, is that we use model-based learning. The idea of model-based learning to help us to create a generative model. And we use VAE and this generative model. And this work is also published in SIGGRAPH Asia 2022. So here is the preliminary results. We can see like after the learning, the character can interact with the environment. We can throw balls to it. We can push it, and the character, when it interacts with the environment, it automatically changes motion based on its states. The basic idea is like on real simulation. We pose actual the character states advances based on this action, and the user simulator and the simulation will advance based on this input and compute the next states, and this will keep going and to generate a long sequence based on the user inputs. And then some recent work, especially the super track that was a SIGGRAPH 2021 work that tells us that this approximation can be done by simply learning a neural network. So which we call it a word model. So it works just like simulator. This word model also takes the states and the action as input and predict the next states. So this whole process is, because the word model is a neural network, so this whole process is differentiable. So we can generate a long sequence using the word model and compare this long sequence with the real simulation. And this can help us to train this word model to approximate the real simulator. So here is one example. So although we think the word model, we originally thought this word model can be inaccurate, but in fact it's pretty accurate. It's accurate enough to capture the real simulation pretty well. So based on the word model, we can now try to train these motion embeddings or these generative models using with the help of this differentiable word model or differential simulator. So the process is very similar to a generative model or VAE. So we know VAE has an encoder and a decoder. So if given it a pose, the encoder will first map into an embedding space and then decode them to recover the original motion. And on the runtime, we can get rid of the encoder and only have the decoder to convert a sample from the embedding space to the motion. And this is exactly the idea of motion VAE, that is kinematic-based method, where it takes two example pose as input and then computes a embedding pose embedding, and then use the decoder to reconstruct the motion. If we take this encoder, we can think how we can convert this process into a physics-based method. So we can consider for the way the kinematic-based method create a next pose is directly use the network to compute the next pose. But for the physics-based method, the problem is a little bit more complicated. We need to use the control policy to compute action and use an action to drive the character in the simulator to compute the next states. So we can consider this control policy and the simulator as the decoder of motion VAE. And now we also have the word model that can approximate the simulator. So we can use this word model during the training to train this control policy. And after that, after training, we can disable this word model and use the simulator and runtime. So the training of this control VAE becomes very similar. This VAE structure is very similar to the control to the training of normal VAE, where we just use this to create a sequence by keep executing the policy and keep executing the word model, and then let it generate the motion to be as close as possible to the reference. So here the word model is phrased. We only train the control policy. And after training, the control policy already has a motion embedding, and then we can sample from that embedding space and convert that sample use the controller into a control signal, and then use a real simulator to drive the simulation. So here are some results that we can just randomly sample from that embedding space and convert them to a number of motions. But here we can see the motion quality is not very good. The problem is that if it is directly disabled, during the training, the encoder knows the desired states and the current states. It will compute a computer encoding the latent variables. But after training, we disable the encoder and directly sample from the latent space. And at that moment, this latent space do not know anything about the input states. So that means there's no feedback to help it to correct any errors accumulated during the simulation. So to help to mitigate these problems, we actually introduce another network that we call as the as the state dependent prior. So it's like different from the original VE, which used N01, the standard normal distribution as its latent distribution. We actually make this normal distribution conditioned on the current states. So this way, it helps the prior and the control policy knows the current states, so it can help the motion, the controller to create a more consistent and more natural motion results. So here's our two examples. The first one is learned using the original VE, the standard normal distribution, and the curves here is a motion. It's a latent code of a single motion in its latent space. We can say it's quite messy, but if we use that state condition prior, the motion, each of the motion is looks more consistent, and that also leads to a better, a smoother motion. So the whole pipeline is seen like this. We first collect some samples and use those samples to train the word model. And then we use the word model to train the policy. So we interleave these two processes. That means we do not train the word model to the most accurate, but we just keep generating new samples using the current policy and use that samples to update the word model and use a new word model to update policy. And it becomes a loop. So here are some results. So using that training, we can generate a state skill embedding, and then we sample from that skill embedding, we can generate a diverse set of actions during simulation. And also the word model, because it's accurately captures the real simulation. So we can actually train a downstream task with the help of that word model. For example, we can give it a controller a control signal, such as I want the character to move forward and a certain speed, and then we use that word model to generate a sequence, and then we measure whether that sequence consists with the control signal, and we use this information to update a high-level policy, then generating then choosing the proper scale in an embedding space. It can help us to finish these downstream tasks. So and then here are some results. So we can use this word model with this model-based learning to train high-level policies to operate in the embedding space to make the character follows the control signals. Like we can go different directions, we can do different actions. And also using the word model, we can see like it can achieve a higher performance than the model-free method in a shorter time on these downstream tasks. Now, actually, we can train that moving the direction control in half an hour, but to achieve the same level of performance, the model-free method like PPO, they need 3 hours at least to finish the task. Okay, so here are some more results. We can do direction control and hiding control. We can train high-level policies to let the character to run and stop at certain target positions, and also we can make the character to resist to external perturbations, and it generates automatically generate natural response to the perturbation. So to conclude, so in this work, we have presented a model-based method to train a generative models. These generative models can combine with the word model to achieve a very efficient training of downstream tasks. But definitely there are some limitations. Currently we still encounter some issues when scaling up to a larger data set. The training data we use for the demos, it contains only 15 minutes motion. We try to use that for 1 hour motion. We find that the results is not as good as we expected. So we think that it might be related to the technical structure, because currently we only use a very simple MLP. So using a more complex network may help. and also improving, replacing that VAE to a VQ VAE, maybe another ways to improve the quality. And that exactly the very what's next. We can do. The first is like whether we can train a ChatGPT level of this kind of motion model. We can call it a digital cerebellum. Basically like how the animals cerebellum is related to their emotion. If we can do that, we can use that to do very interesting things. Another thing is whether we can combine this with large language models such as ChatGPT. So actually, this is very interesting experiments we have done with ChatGPT, where we let ChatGPT, we tell it to create a action sequence, then it can make the character move out of a rule. So it actually gives a sequence of actions. And then we can think like whether we can convert these sequence actions into a sequence of motions, and then the automatically becomes a performance. So then that will be very interesting topics to explore in the future. Okay, that's all of my talk. Sorry for it's a bit long.
Thanks so much, Livin, for your excellent talk. And I think both of the paper are very practical technique for automatic motion generation. Since we are out of time, let me ask a quick question, maybe about the first talk. Like from the Obama speech example, I see there are some motions like the character pointing to the left first and then pointing to the right, after. So because people have some symmetric character properties, so will this bring some ambiguity issue when you do the training or not?
I think because we have our network structure design. In the representation of our motion model, we see that there's actually a style code that captures this kind of variations. So after training, we can definitely this is a problem, but using this the style code, we can make this not that much, but it's still but it definitely, but that's true. That might be has these ambiguity issues. Yeah, but I think for these demos, I think another issues is also if you see these motions for a long time, you may find that this character tries to overact. That means it always perform gestures, but for real person, real human, they will not do this all that much. So that is one of the limitation of this work. But I think that we might need another ways to predict whether the character need to do the gesture or not.
Okay, so maybe let me ask the last question. So how you evaluate the motion or the gesture is natural or not?
Well, I believe this is a very tough question. I mean, if you ask any people who do motion generation or rendering, they will have the same issue. What is the best results? Honestly, no, we don't have other ways to do this. So actually, for all of our work, we usually rely on human. We do user study. We collect. We recruit a number of people who help us to score the output motion. But I think the way ChatGPT is trained, maybe a ways to help this problem. Like we can possibly recruit hundreds of people to do the scoring task, and then use that results to train a discriminator to help us. That might be a possible way to do this.
Okay, this is a very inspiring suggestion. I think we're out of time, and that's all about today's seminar. And let me thank all of our speakers for their excellent talk and also the inspiring discussions. And also, I want to thank all the audience for your watching. And bye-bye. Have a nice day.
Thank you. Have a nice day.
Bye.
Bye-bye.
Bye-bye.
Wait. 喂。